Good morning, good afternoon, and good evening, wherever you are. I'd like to start by welcoming everyone to this non-volatile Memory Express sponsored presentation. In today's webinar, we'll be taking a deep dive into the history of NVMe protocol and how it's been designed to be deployed anywhere. Before we jump into the presentation, I'd like to give you a quick reminder, cover some BrightTalk user interfaces. First, some of the graphics and text within the presentation might be slightly small, so I'd recommend enlarging your viewing area to full screen. This can be accomplished by clicking on the outline box in the upper right-hand corner of your window. I'd like to also encourage everyone to make this presentation interactive by asking questions of your presenters. You'll find a chat box in the right-hand side. You can recognize this by the question mark. We have a full agenda today, so in order to make sure we get through the presentation completely in the time allowed, we'll be holding all the questions and answers until the end. Also, we're going to get requests for the presentation, which we will be making available from the NVMe website after the webinar. Real quick introductions. My name is Tim Lustig. I work at NVIDIA and also reside at the Nvme Express Marketing Committee. I'm joined today by two Nvme Technology experts, one from NVIDIA and one from Cisco. We'll be discussing the origins of the Nvme standard and its adoption to a multi-transport technology with the development of Nvme over fabrics, and where this fits and where this transport technology fits in today's data centers. First, I'd like to welcome Camille Bakshay, who is the Director of Storage Transportation Solutions, a technical marketing group in Cisco Systems. He has over 35 years of experience in networking technologies related to campus, data center, IBM, storage area networking. His experience includes companies like Apple Computers, Bell Labs, 3Com, Arista Networks, and he is a member of the Nvme Express Promoters Group. Also joining us today is Rob Davis, who's the Vice President of Storage Technologies at NVIDIA Networking, where he focuses on ways to apply high-speed interface technologies to storage systems, as well as having key roles as an evaluator of emerging technologies, products, and relevant markets, including NVMe Express. With that said, I'd like to turn the presentation over to Camille to take us through the first part of the presentation.
Thank you, Tim. To give you an example, let's talk about the history of NVMe, right? So to give you an example, an idea that NVMe by 2025 will be $100 billion total addressable marketing. So it's an innovation that is exploding, right? So it's a technology that is related to storage, and storage got started back in 1960s with IBM mainframes, right? So now, the System 360 was that. At that time, the mainframe ran multiple applications. Then, not until 1980, then IBM introduced IBM PC, an open architecture based on Intel's 8086 architecture, the x86 architecture that dates back to 1978. The PC kind of over the years evolved to XT and AT, AT being the 16-bit internal bus with the called ISA on it. The interface between the motherboard and the disk drive was called IDE, right? Integrated Device Electronics. And then in 86, SCSI also came into the picture. NCR Sons and servers, they make the architecture, the SCSI was on that. Actually, SCSI came way back then from Sugar Associates back in 1978, right? Now, IDE inside made it standardized to ATA attachment protocol. Actually, it's called parallel ATA at that time. The parallel SCSI, it was only 18 inches long, right? So serialization efforts started for that for enterprise businesses. So fiber channel came into the picture back in 90s, right? The fiber channel protocol mapping came into there. So mainframe SCON protocol got mapped into fiber channel called FICON. SCSI got mapped into called FCP. SCSI in there. The clone industry was going on. IBM was with the MCA architecture. Other industry, the clone industry started out extended ISA architecture. That becomes standardization. Intel back in 1990 came out with a computer bus called PCIe. It actually uses the sets of registers to communicate with the peripheral devices, port mapped or memory mapped and all that. NAND started to appear as a flash memory, Toshiba back in 1987. Intel introduced NOR flash also. In fact, the first ATA flash disk drive was launched by Intel back in 1993. It was only 10 megabyte. They launched it with Corner company. Then what happened is that the flash was not fast enough, right? before even we go to that, the ATA PI architecture came into the place, right? The packet interface. ATA was for disks, so the PI packet interface was for other devices like tape, the removable media in there, right? And then the serialization of the SATA happens, ATA happens, called SATA in there. And then in 2003, Intel introduced a new programming model for the SATA. They call it Advanced Host Controller Interface, AHCI. In fact, the first version came out was written by Amber Huffman, who is the current president of the NVMe also. So this AHCI, it was a PCI class device interface for moving data between system memory and SATA. Serialization of the SCSI starts to happen. SAS came along. Infiniband came into the picture. In fact, they mapped SCSI over Rdma. SRP protocol came along. All-flash array, first all-flash array came along. Multiple companies, including Violin and all that. Then the Open NAND Flash Interface Working Group got started. The Flash, SATA SSDs and SAS SSDs starts to appear in there, right? Now, the performance with the SATAs and SAS SSDs were not that much. So Intel started to look at what can we do. So they took at the AHCI architecture and start to see that whether we can do something with the non-volatile memory for this host controller interface, right? So they defined the NVMe HCI back in 2008. Again, Amber Huffman, initial version was written by her, lead author on it. So this NVMe HCI it's again a PCI register level interface allowing the host and NVMe subsystem to communicate using port mapped IOs, right? And then in around the same time, 2009 and 10, another group within the Intel, in fact, they were working on a project called Aeon. They were working on this project to expose storage directly to the user space for the better performance, right? So they were using some Infiniband concepts, the queuing architectures from Q-pair architecture. They called it IO queues and admin queues. They came up with the doorbell architecture and also with the PRP, right, physical region pages and all that. But that group got merged with NVMe HCI, and then the group redesigned all the queuing architecture back to the MSI interrupts in there, pushed the whole interface back into the kernel, and then came along the first version of NVMe 1.0 back in 2011. Again, the lead author for this one was Amber Huffman. It was 100-page long in there. In 2013, Samsung introduced the NVMe SSD among other companies. In 2014, NVMe got incorporated as NVMe INC, right? So NVMe transport protocols came into the life, right? In 2016, RDMA came into with Infiniband over UDP, Rocky, over TCP, IWAP. T11 took the fiber channel and they mapped that into fiber channel 2016, right? The NVMe-FC. And then the TCP in 2019 came along. Now this year, NVMe 2.0 will be coming out very soon. That will rearrange the spec, divided into 4 categories. Base spec will have core NVMe and NVMe-oF. The command sets, the second set will have block, ZNS, key value. Third will have a transport-specific PCI, RDMA, and TCP. And the fourth one will have the management in there. So this is a brief history of NVMe. Back to you, Rob.
Thank you, Kamal, and hello, everybody. So let's up-level just a bit. So as Kamal said, NVMe over fabrics, which we're going to go into depth on in this talk, all starts with Nvme technology. This is the SSD interface that Kamal described that was designed from the ground up for SSDs, eliminating all those legacies that came before it that were designed really for hard drive interfaces. This is the interface that these hard drive interfaces, SAS and SATA, were the original ones that were used for SSDs when they first came out with the NAND technology. Because these legacy interfaces were designed for hard drives, they had numerous bottlenecks when you connected them to SSDs, which the NAND technology behind them was so much faster than the spinning of electrical mechanical devices in the hard drive media. So by eliminating this, the NVMe performance was dramatically improved. And this chart compares the performance of early Samsung NVMe SSDs that had both SATA a hard drive interface and NVMe interface on it. The rest of the design was identical. So it perfectly shows the advantages of this new NVMe technology, the new NVMe interface. Now, NVMe over Fabrics takes this new high-performance SSD interface and enables it to be connected remotely across a network. And this gives us all kinds of advantages over local storage. It's now infinitely scalable, very efficient from a power, cooling, and rack space perspective, and much easier to manage than local storage. These are all the things that SANs were invented for with Fiber Channel, you know, back many years ago in the 90s. The standard was developed by storage vendors from all across the industry. Many were the same that worked on NVMe, and it was done in the NVMe.org organization, and version 1 of it came out in 2016. Some vendors, including Mellanox, of course now part of NVIDIA, were demonstrating early versions of the standard before this. This one was actually at the NAB show, the National Broadcasters Association show in Las Vegas in 2015. Even though the storage is now on the other side of the network with NVMe over Fabrics, the performance is very close to NVMe performance, local NVMe performance. And this chart shows this using straight open source Linux NVMe over Fabrics software on both the initiator and the target that was released with version 1 of the standard. And it has 100 gigabit NVIDIA NICs in x86 servers. And you can see near wire speed and 6 million IOPS. And this was way back in 2016. This performance is much, much better now. Back over to you, Kamal.
Thank you. I was just Googling before coming onto this chat that how big NVMe market has become, you know, since the introduction in 2011, the initial spec. According to almost all research, it shows that it is going to be over $150 billion by 2025 and beyond, right? So it's a huge. So it came over last 10 years. So let me give you a little idea of what was going on. Back in 2011, NVMe started with the queuing interface designed into the memory, right? There was a PRP pages used. Then the NVMe starts to take the problems within the flash storage and start to solve that. Multipathing was added in there, scatter gatherers were added in there. Then, you know, host memory buffers. Now, in the flash systems, you have DRAMs, and if some cheaper flash don't have the DRAMs, SSDs in there, DRAMs, then what you can use is NVMe allows you the HMB, like the host memory buffers, where you can use the memory out of the flash to use that to your LBA translations and all that. Similarly, the controller memory buffer, a great architecture where instead of placing your queues within the memory architecture, you placed it into the SSD so that when the information is transferred, you take the system memory out of the picture, you know, just reducing the latency. So as you see, as NVMe grew, every year they took a problem and solved it. Back in 2016, they said now NVMe is within PCI bus. How can we take it outside of the PCI bus? How can we take it to the network? So rather than inventing a new network, they looked at the transports at that, you know, Infiniband. They look at fiber channel. They look at IP network and Ethernet, and then they mapped. So first version came out with Rdma binding. It was on Infiniband natively, and also on the IP with the UDP with Rocky, and then the TCP with IWAP in there, right? They defined the method to map it in there, but the transport remains the same, whatever the transport was, the connect methods and all that. And then again, you know, major thing happened in 2019 when we put the TCP transport binding in there, you know. So, and then again, you know, soon NVMe 2.0 will come out, and with that, there you take the base spec, you put the core of the NVMe and NVMe-oF commands in there. You take the command set in a separate things with now with the command sets are expanded to block to zone namespace to key values, and then another spec will be on the transport where the PCI, RDMA, TCP, and then the management spec. The goal here is for the next version of NVMe is to simplify the adoption by creating this separate standard so that people can take what they need to implement and implement it. So as you can see, what NVMe is doing is it is solving industry's problem. As in the first generation, it took the PCI bus mapped into the SSD storage, and hence it became very fast, right? As fast as the PCI can go, as fast your storage access is over the flash. Then they solved the problem of taking NVMe over the transports and mapped it to all the industry available transports. And hence NVMe is now more especially like a composable data center, right? You can use that. Next, what NVMe is doing is they have a technical work task force looking into it's a storage, right? So NVMe storage. So now the computation, the compute powers are being put on the storage. And pretty sure Rob will talk about DPUs, GPUs. Then that capacity can analyze the storage. That's where the computational storage is. That's what NVMe is solving next. Rob, back to you.
Thanks, Kamal. And I think it's important to just reiterate this one particular uniqueness of NVMe over fabrics. This standard, the NVMe over fabric standard, is not tied to a specific wire technology like most of the others are. It was purposely designed from the beginning to be fabric independent. To accomplish this, there is a component of the standard called the transport binding specification. The first transport binding spec was for Rdma, and you can notice that this is not even tied to one wire protocol either. So the Rdma transport binding spec can be either Infiniband or Ethernet, and actually two different protocols on Ethernet with Rocky and IWAR. So very unique standard from the perspective that it defines how the data is organized and verified across the network and all those kind of typical storage functions, but it doesn't care what the transport or the wire that it runs on. It was actually planned from the beginning that most of the fabrics and protocols could be added. It was all set up for this right from the beginning, like the fiber channel and the TCP that were added afterwards. Back to you, Kamal.
Okay, so let's look inside of the architecture of NVMe. Now, this is very important because it's a very simple architecture which allows the communication, how the storage is stored, right? Now let's go with the thing. Here I'm showing you a host inside. There's an application. Let's say there's a Linux involved in there. Next. So first thing the application is going to do is it's going to submit its request. Let's say it's a read request. It's going to submit it into and NVMe has this SQ-CQ pair. Maybe I should go and explain where does the SQ-CQ comes in. So let me digress here a little bit. So when the host powers on, during the init process, the NVMe init function is called, and that will call the probe functions within the PCI initialization. The probe function will initialize the hardware, NVMe, allocate the resources. It will register the device with the kernel as a block device, and then we'll set up some PCI config register spaces, right? The class code is defined as an NVMe device. The base address registers, the bar will be set, pointing towards the NVMe controllers, and that's where the NVMe, SQ-CQs, doorbells, all that information is stored, which is, all those queues are created through NVMe create IO commands, and admin commands actually helps do that. So now once the CQ and doorbells and all those things are there, now let's get back to there where, number one, the submit IO is done next. And then what is going to happen is that the system has to tell the controller that I have done something. So it'll ring the doorbell next. And then the controller will go in next, and the controller will go and fetch the command and execute the command, right? Let's say some writing data, reading the data from there next. And now what is going to happen is that once the IO is completed, once the data is read, it will say, I have completed the thing. And now I need to go back, tell the host that I have finished reading the data next. So it does an interrupt, right? We use the MSIX interrupts in there. And once the interrupt is done there, the host is going to make sure that there was no errors and all that, and it'll finish reading it, and it will go ahead and ring the completion queue. So now that was if the storage was at the local. So we're using NVMe PCI. What if the storage, the flash, SSDs is not local, if it's remote over the transport? So now this NVMe transport controller is remote sitting in there, right? Now how does this thing should happen? As I said earlier, NVMe-oF took the transport bindings, it took the existing networks next, and then they mapped all these transports, NVMe commands over the existing transports. And I'm showing you 4 different things in here. Infiniband architecture. Within Infiniband architecture, you already know that the Rdma, the concept of queue pairs was already there, right? So Infiniband has this send and receive queue, and the CQE, right? The completion queue entity in there. And then within the UDP, when you take that Infiniband transport headers map into UDP, that becomes your Rocky, flavor in there. And then for fiber channel, there's a fiber channel protocol which was designed to map multiple workloads on top of it, SCSI, mainframes, anything like that. So now NVMe is mapped into the fiber channel also. And then again for the TCP transport binding. The transport connection piece next. The transport connection piece is left up to the network guys, however they communicate, same transmission headers are used. Now within the host, you have another driver which is called NVMe-oF, right? Depending upon what are you loading. You have a Rocky driver, you have fiber channel, you have NVMe TCP drivers in there. All the commands are encapsulated. So whatever NVMe commands were used in the local, majority of the spec remains the same, right? If we just add more the transport spec with NVMe-oF, right? So now, in the transport piece, every NVMe commands will be mapped into the capsule next, and then it will be transmitted over to the remote side. Now, in the PCIe local NVMe, during the init routine, all the queues were created, SQ, How are we going to create remotely all these queues and maps, right? So this is where the NVMe, the OF commands comes into the place. If I divide the NVMe command sets, I can divide into 3 categories, right? There's a basic NVMe IO command like read, write, flush, and so forth, right? Then there's NVMe admin commands. Now, admin and IO queues, they're both, there's an admin SQ, CQ, there's an IO SQ, CQ. Admin is the one which gets started first for the controller, and then it creates the rest of the IO queues, right? So there's admin commands like create IOs and get feature, set feature, and so on. And then there is an NVMe-oF commands like connect and disconnect. So this is the connect and disconnect where the SQ, CQ pairs gets created. So the flow will go like this. When you start NVMe TCP, for example, or NVMe Rocky, for that matter of fact, the transport connect, whatever the Rocky connections are, that will go in, connection will be established. Then the NVMe connector will go on top of it. That's where the remote SQ, CQ pairs will be defined. And then if the session is disconnected, NVMe disconnect will go, it will take down the SQ, CQ pairs. And then, the whole NVMe session can take place. Next. Now, there is some key features about it is that there's a one-on-one mapping. This is a little bit different than what NVMe PCI is. NVMe-oF has a little bit of a different in there. I will highly recommend to read the spec. You guys go ahead and read the spec for the detailed differences in there. But let me follow you. Let me tell you exactly what I did early on. I'm sorry, I don't have the diagram for it. We're going to stay on this diagram and tell you how a read command will be executed over this now with NVMe-oF. So the host on the left side will be sending out IO reads. It'll be translated into wiki in the block MQ. It'll go out, ring the doorbell to the HBA. Is going to say, go ahead, the HCA. It's going to go ahead. And the fabric send command will go out inside the capsule to the controller side of it in there, right? And now the controller side, the HCA will look at it and he will say, oh, I have I'll post the IO, it will interrupt MSI, right? And then what will happen is that the system will ring the doorbell, and then the information will be, from the SSDs, from the remote controller will be fetched into the system memory of the remote controller. And then from that point on, that remote memory will come down all the way into the host. And then in the back again, the host again, the same thing will happen. The interrupts will be, MSI will be done. And then the host will kind of read the fetch, the whole thing. Interesting thing about RDMA is since the Infiniband, the NVMe is based on Infiniband queue pairs, they took that concept. Obviously, they did it differently a little bit. But within the RDMA, Rocky, for example, the NVMe SQ-CQs will be identically mapped to the queue pairs within the NVMe Rocky, and it makes it a very nice pairing in there. Now, next. So if you look at the storage architecture within the data center, right, there's multiple things going on, right, over the years. There's a FICON storage, there is mapped into, there's a single byte commands mapped into fiber channel. There's a SCSI protocol, predominantly with enterprise networks. So that's mapped into with iSCSI if you go in the transport, or in the ISER, or if and then the NVMe come out. Actually, at that point, there could be SRP also mapped into the Infiniband. And when NVMe came along to make the flash, performance latency lowers, then NVMe over Fabric protocol we mapped into an Infiniband, Fiber Channel, Rocky, Next, IWOP, and TCP. So this is where beauty of NVMe-oF is. It is not dictating you to pick any particular transport. It is saying based on your workload, you can pick any transport that suits your needs, your criteria, right? So for supercomputing, you want to use Infiniband, great. You want traditional fiber channel applications, which people are very comfortable with, all the world's banking, financials, and all that going over fiber channel. They used NVMe fiber channel. If you want to do as NVMe TCP, which is widely available, if you want to build a composable data center, you can use that. Next. So if I give you a little bit of an idea how the advantages are, let's build the whole slide. Next. If I give you some idea that the fiber channel, Infiniband, and Ethernet transport, one more. So mainframes were there early in the beginning, right? And they had the bus and tag, went on to the SCON, the serialization. And then when the fiber channel came along, they mapped all that, CKD, key count data into a fiber channel, called it FICON. So that's still available today. A majority of a lot of mainframes, a lot of transactions happen in there. Fiber channel also there's FCP layer on top, maps SCSI into it. And that's where the NVMe got mapped in there. Now the NVMe fiber channel, there's a newer version, fiber channel 2. That's where they take care of some of the advanced error detection and recovery. There's a slur protocol in there. It's a sequence level error recovery. In other words, is that when the fiber channel sequence, that's how the NVMe commands goes into the transactions, the exchanges. When there's any error at the fiber channel level, earlier in the first version, it will disconnect the NVMe session, then you have to reconnect it again. But now, if there's any sequence level error, it will not disconnect your NVMe session, will go on, right? But then with the TCP, which has just become, I think last year, just before that, available, the standard, it makes, you can use either lossless TCP or you can use loosey TCP and extend your composable data center. And then with the Infiniband, I'll hand over to Rob to talk about that.
Sure, thanks, Kamal. Yeah, thanks, Kamal. So with Infiniband, of course, you get the focus is on supercomputers, but also now with GPUs, there's a lot of focus there as well, especially because AI and machine learning applications have moved into sort of the supercomputer category. And so RDMA, as I'm going to show later, is super important to moving data in and out of GPUs at high performance for the obvious reasons. And then with Rocky, which runs over Ethernet, you have the ability to do almost the same capabilities, and I'll show details on that across Ethernet with RDMA over Ethernet or Rocky.
Next, Rob, it's you.
Yeah, so just to kind of up level a little bit what Kamal was going into, the way down into the depths where of course a lot of the audience wants to hear the bits and bytes, but to kind of up level it for RDMA anyway, the Rdma Transport, here's how it works with NVMe over fabrics across a network. And this is why it's almost as fast as a local NVMe SSD. And it does this by encapsulating the local NVMe commands inside the NVMe over Fabric protocol. It's a really close match, as Kamal showed, and then it sends it across the network and then de-encapsulates them, and it sends them to the remote SSD. So the remote SSD doesn't even know the network is there. The protocol bypasses the legacy storage stacks when the Rdma transport is used on Infiniband or Ethernet. RDMA is the remote version of DMA. We didn't go into details on this, so I'll explain it a little bit more. So that's, it stands for direct memory access. And this is the hardware, this is a hardware-driven transfer of data from memory to memory within a computer system. It's basically an offload engine, so you don't have to sit in a software loop and move data one word at a time. What RDMA is the remote version of that. It's a hardware-driven memory to memory transfer across a network performed by either the Infiniband or the Ethernet adapter on each side. That's where the hardware engine is. So basically you give that adapter a pointer in memory. There's a registered memory on the other side, and those adapters move that data without any interaction of the computer, the CPUs on either end. Instead of the network transport layer being in software like it is with TCP, the transport layer being what guarantees the delivery, retries if it isn't, etc. With Rdma, all that is in hardware on the network adapter. So that's why you get the lowest latency, the highest bandwidth, and you lower the CPU utilization because there's no transport being run, no transport stack like TCP being run, which when you get into speeds of 200 and 400 gig can take a lot of CPU cycles. All the first NVMe over Fabric products and demos were done with Rdma, since it was the first transport binding spec that came out, and it's still to this day where you get the highest performance. Just so when looking at the last slide, you might have wondered what the performance difference is between Rocky, Rdma over Ethernet, and Infiniband, to which Rdma is the native protocol, as Kamal pointed out. And that is, in a nutshell, the difference. Because IP is the native protocol on Ethernet, Rdma sits on top of IP there. And that adds a small amount of latency, which you don't get in Infiniband, where Rdma is the native protocol. From a bandwidth perspective, they are pretty much the same, assuming identical wire speeds anyway. The difference comes in that added latency. IB, because Rdma is native and because the switches and adapters, the hardware was designed originally for HPC, where you're clustering computers to make a bigger one, so latency is super important. It has less latency, around a half a microsecond difference, as you can see on the chart on the left, which is looking at RNICs. Whereas the best RNICs are, that's about a half a microsecond more, depending on the NIC vendor, of course. This shows this chart is comparing an identical Infiniband and Ethernet adapters. NVIDIA makes adapters that can run both protocols. So it's the same adapter, just running Ethernet in one case and Infiniband in the other. But one thing you have to keep in mind is when you add switches, which is the chart on the right, you add more latency. Again, depending on the switch vendor, of course. It doesn't seem like much, a few microseconds, but it adds up when you consider that the fastest SSDs, like 3D Crosspoint ones, for example, have less than 10 microseconds of latency. And keep in mind, you need to pass through the switch and adapters at least twice in each read and write transaction, right? Because it's a request response protocol. Also, there's often 3 or more switches in the data path. So if you're not paying attention to your NICs and switch latency performance, it can easily double the latency of your SSD. So next, I'm going to talk about where all these high performance, all these different transports fit into the data center wide architecture. And this gets a little bit complicated. So let's take it one transport at a time, starting with the easiest one, which is NVMe over TCP, even though it's really the last one to come out of the standards group. And the reason it's easiest because it can basically work anywhere. At NVIDIA, for example, we've run it from our lab in Israel to our lab in Sunnyvale across the internet. As you can imagine, the performance was not so good. And really, performance and cost are the real determining factors here for what transport to use and where. Because with varying amounts of effort and a few exceptions, you can make any of the transports work in most situations. But one of those exceptions is data center to data center. So for connections across the world, NVMe over TCP is probably the best choice. But if you look at GPU clusters, you must have Infiniband or Rocky in order for GPU direct storage, which I'll talk about in detail coming up, which enables you to get the highest performance when interfacing storage with GPUs. inside high-end storage systems, and again, I'm going to show you more details on this, but inside the high-end storage systems, most often you'll find Infiniband or Rocky as well. And then if you move up a level and look at across data center, you can find fiber channel, TCP, Rocky, and in HPC data centers, of course, Infiniband. And all of those can be done at scale. Rocky at scale takes a higher level of network expertise than IP, but it's widely used in hyperscalers, which have the biggest data centers in the world. So obviously it can be done. And we have, there's many, many customers of my company that are doing that today. And for more in-depth on all of that and how it works, I'm going to turn it back over to Kamal.
Thank you, Rob. So as Rob was describing that the high-performance computing with RDMA, with Rockies, and Q-pair mapped into NVMe. Also, over the years, the TCP adapters have come along a long way, right? So here I'm showing you a picture of an enterprise data center. So the TCP adapters with the smart NICs coming along to the place, they're offloading a lot of the TCP stacks, segment loading, TLS, and all that on the adapter itself. And with the magic of DPDK and SPDK, almost the performance is reaching to the very, very, very better performance than whatever it was possible with the NVMe TCPs also. So looking at this data center enterprise, I divided into different, like 6 pods in there. The fiber channel, in the history, what happened is that the fiber channel became the de facto standard for all the major banking financial applications because of the high availability, because of the reliability and the security provided in there, and the performance. If you look at fiber channel, we're launching 64 gig now. The industry is going through that, right? And why the Ethernet is going on to the 400, planning on 800. So speed was not very important to the customers. Of course, it's important, but the other applications running on the fiber channel, the infrastructure, the services, the storage services, the fiber channel services like discovery, name services, and zoning, and all that was much more important, and hence they slowly moved towards the speed. Next, in part 2, I'm showing you how you can connect some of these NVMe, like for example NVMe fiber channel storage array directly to a top of the rack IP switch. And the IP switch can, in this case, of course, I'm showing you one of the vendors like Cisco MDS switch here, 9K, which can do fiber channel and IP also, so that if you don't want to use any fiber channel switch, you can take the NVMe fiber channel array, directly attach it to the top of the rack 9K switches. In part 3, I'm showing you that the hyperconverged infrastructure guys, which they converged everything into a single computer kind of a thing, now are going back and disaggregating it a little bit, where they take a compute node and a storage node separate, right? So for the storage node, let's say they're using NVMe SSD on the storage node. Now to connect the two, the compute to the storage, again, NVMe-oF will be utilized in that case also. So those instances are coming into the picture now. And as Rob was saying, that if you want to put onto the Ethernet, the UDP, the Rocky, one can deploy within the rack, right? Where I won't recommend put the Rocky NVMe outside of the rack, just below the top of the rack, put it in the rack, and it will work outside of the rack also, but just do the within the rack. That works better. That's the best practices are. And if you're going to scale it out, do it with the TCP and so forth. So again, the summary of this slide is that the NVMe technology is really allowing customers to take full advantage of their infrastructure investments, whether it's in the fiber channel or Ethernet at the same time, not restricted to either one of that. And also, soon companies will start providing a single dashboard to give you the visibility end-to-end of NVMe-oF flows for you. Next to you, Rob.
Awesome. So I'm going to dig a little deeper into some of the applications now. This was the first application for NVMe over Fabrics to go to market. And it's kind of interesting because probably most of the world doesn't know that inside many of the especially the high-end all-flash array systems, these are the rack-sized, refrigerator-sized ones. They have capacity expansion JBOFs connected over a hidden network or fabric, usually totally inside the enclosure, so you don't even know it's there. And here NVMe over Fabrics has replaced much of the PCIe and SAS fabrics that used to be there in earlier designs, with either Infiniband or Ethernet fabrics using NVMe over Fabrics on Rdma. They use the Rdma because it provides, first of all, they're using at least 100 gigabit, if not more, and it provides the high performance needed to support NVMe SSDs. Because an NVMe SSD, even with Gen 3 one, can do almost 20 gigabits per second, and Gen 4 is all drives are already available, which are double that, and Gen 5, of course, is on the horizon. And it's also more scalable and flexible for high availability than PCIe and SAS was. So RDMA protocol provides the consistent low latency needed for this application, and it's that consistent latency that's super important when you've got a storage backbone for these kind of systems. And what's kind of ironic is a lot of the other transports and technologies for storage that are out there today, like, and have been for years, like Fiber Channel and iSCSI, for example, inside those systems, there's NVMe over Fabrics on RDMA providing the data from the actual storage shelves that is then being transmitted to the users over Fiber Channel and Ethernet with SCSI protocols. The next application I'm going to show is one that's really interesting now in the world of cloud, whether it's private cloud or more hyperscaler kind of size. And this application is really enabled by the performance that NVMe over Fabric gives. That's very close to local storage performance. Here, instead of having compute nodes in the data center configured with the amount of storage and compute needed for each application, you disaggregate the compute from the storage using NVMe over Fabrics. Now, depending on the application, storage and compute needs, whatever that application needs in those areas, you use the network to provide them just by configuring the amount of storage to the different compute node. And now that your storage is networked, you also get all the advantages of network storage, the scalability, the better storage utilization, usually about a 40% improvement, and much more efficiency for power, cooling, and rack space. And it's also much easier to manage all the things that we talked about earlier that NVMe over Fabrics brings from the world of SANs. And here is the last application I'm going to go into a little bit more depth on. And it's something called GPU direct storage that I mentioned earlier. So if you look at the top of the slide, before GPU direct storage came along, the network storage data path for GPUs worked like the top of the slide. The storage data is read directly. The storage data in the read direction is first moved from that SSD on the storage system into the memory of the SSD driver, then to the storage stack, then move to the memory of the network stack on the out to move out of that initiator, all flash array or file or whatever is the system on the end. Then the network adapter takes it across the network where it moves into the network stack of the GPU's host CPU, which moves it to the host memory where the artificial intelligence, machine learning, whatever the GPU application is, can now move it to the GPU memory. So there's lots of memory moves and software getting in the way of the performance. With GPU direct storage, which is shown on the bottom here, most of those data moves are eliminated. And the data is moved with the two network adapters using RDMA, their RDMA hardware offload, from the SSD driver memory in the storage system to the GPU memory across the network. This, of course, increases the performance of the GPU application dramatically in IOPS, in bandwidth, and in latency, and it reduces the CPU utilization of that host. But it does require RDMA because that's the only way you can move from memory to memory and bypass all those different buffers and software stacks. And so it requires protocols like NVMe over Fabrics. in the future, it will also be possible to eliminate the storage system moves with a new NVMe org standardized technology that's now starting to become available in SSDs, and that's called Control Memory Buffer, or CMB for short. And this allows the Rdma hardware engine in the network adapter on that storage system to move the data directly from the SSD or to the SSD in the other direction across the PCI bus, and it never has to go through system memory. And there's another technology called eBOF, and the same is true there. That's where instead of a PCI interface on the SSD, you have an Ethernet interface. And this is another new technology that's on the horizon, which again, just further improves using RDMA, the performance in and out of GPUs for HPC, machine learning, artificial intelligence applications. And with that, I'm going to turn it back to Kamal for
Thank you, Rob.
A detailed look. Yeah, go ahead.
Yes, I'm showing here, so NVMe over Fabric, I take a particular example of NVMe fiber channel. So now NVMe PCI gives you, how you flash access to the SSD access in there. NVMe over Fabric gives you a transport to go over, and fiber channel transport, as I'm showing. So within the fabric, fiber channel fabric, and I'm showing you inside of a switch in here. I'll just a disclaimer: this is a Cisco MDS 97, with the fiber channel ASIC insides. I'm showing you. I'm going to walk you through that how NVMe fiber channel flows. One has to track and be able to extract the analytics information so that you are getting the best performance over the network. It gives you that live real-time analytics processing. Now, you imagine that 64 gig fiber channel is there today. If you have a 48 ports on a line card in a modular architecture, at every port at 64 gig, every packet is coming in. And if there are 8 line cards within a director, every port, every packet, the metadata has to be extracted. So it has to be done on the chip. And that's what in the yellow inside we're saying, that the packet comes in, the fiber channel goes to the parser, goes to the forwarding, goes to the VOQ architecture, virtual output queuing. Arbitration happens to make sure that the egress port is available, packet can be accepted. If it is available, arbitration is given positive go ahead, and now the packet is going to go through the backplane on the other side, and I will describe the whole egress route. The same thing happens. But interesting thing happens here is, while the packet is going through the ingress packet assembly here, which I'm showing, there's an optical tap. There's a tap in there within the ASIC. So in other words, similar to the optical tap, if you want to capture the packets, you can do an optical tap and capture the packets. Here, we are capturing the packet within the ASIC, the metadata of that NVMe-oF, NVMe fiber channel, and then we're extracting on chip itself a hashing table with the both flows, right? You take the initiator, target, learn information, exchange ID, and then on the reverse direction, what the response came back. Now you take all that information, and on board there's an NPU analytics process engine in addition to doing processing on chip. That NPU dedicated for analytics on each line card. So you have 8 line cards, you have 8 NPUs within a switch, and then this switches out to the external connector where you can see this NVMe fiber channel flow from the historical perspective. Imagine you have 10 switches, fiber channel switches, each with the 8 line cards. So there'll be 80 NPU processing the fiber channel analytics. Very powerful thing. Back to you, Rob. Actually, there's one more before back to you. So now, how do you deploy NVMe over Fabric, right? The process has to be very simple. So simply, there's ways to do it. You can do config automation. You can come up with some Python routine. What another way to do that is that the IP switch configurations. Now imagine, fiber channel is very automated. You don't define IP addresses, you don't define anything. You plug it in there, zoning, and the whole thing goes. Similar things have to happen on the NVMe, for example, TCP or RoCE perspective on the IP networks. So let's say you want to deploy NVMe RoCE. You go to your controller. In this case, I'm showing your ACI APIC controller. You say, I want to deploy the NVMe RoCE. You set up which 2 devices, initiator and the storage host port, and then you define a simple contract which says that the what will be the performance, like no drops and things like that, and then you say go. What happens is within the architecture of here ACI, what it is, everything is defined in objects. It's like an object tree. So as you define your intention, what you want to do, that object tree gets mutated, and then that will be pushed down to all the switches automatically, and the switches will create that particular NVMe Rocky configuration automatically on each of the switches in there. So this is a single-click strategy. This is how makes it very easy to deploy NVMe-oF. Back to you, Rob.
Yes, and this is an important thing about NVMe over Fabrics is that it's not, Fiber Channel. I was involved with the standard way back when it began in the 80s, actually late 80s. And so it's a very mature technology. NVMe over Fabrics, right, it came out in 2016, so it's pretty young, but the standard is continuing to improve on the aspects of making it more automated, making it more simple, making it more basically like Fiber Channel from a management perspective. And so there's efforts underway that'll be, that are actually nearing completion to automate how the discovery process occurs and how you can do things that you can already do in SCSI networks, like boot from SAN, where you'll now be able to boot over NVMe over Fabrics, and that'll be all standardized, so it'll be the same across across all the vendors, of course. So now we're going to switch gears a little bit and talk about security. So when NVMe over Fabrics is Ethernet based, there can be a security concern. And that's because in Fiber Channel SANs, it was isolated, right? So it's a totally separate network, totally separate switches. And it was isolated by the servers with different adapters. So the Ethernet from the Ethernet network, which is perceived to be more easily compromised, right? The Ethernet network talks to the WAN, so it must be easier to get at. So one answer is to encrypt the data before it crosses the network. And there's all kinds of efforts underway, of course, part of in the NVMe.org to enable how this encryption is going to work and be standardized. But there's existing Ethernet standards already, like IPsec, TLS, that can already be integrated into NVMe over Fabric traffic. But you need to keep in mind that it can hurt the NVMe over Fabric's performance by adding latency and restricting the bandwidth. Luckily, new adapters and DPUs, data processing units, SmartNICs by another name, today have encryption offload engines in their ASICs, which enables them to encrypt the data on the fly as it's transmitted and received by the servers and storage systems. And also with the DPUs, you can provide security through isolation, which makes it impossible to access the storage or networking without authorization from the DPU software, which in itself is inaccessible from the potentially hacked server. So along with the new efforts, and again, that are almost complete in the NVMe.org to add much more security to NVMe over Fabrics, the existing, in Ethernet anyway, the existing standards, ways to do it, and new ones with devices like DPUs are available today. And back to you.
Yeah, last slide, I'll rush it so that we have some time for question and answer. So as Robert was describing about the security, if you look at the enterprise security in the data center, zero trust model is very popular there, right? So how about if any of the transport, any NVMe-oF, whether it's TCP, IWOP, Rocky, or even if it's a classic iSCSI, how about if we take that data and encapsulate within the VXLAN tunnel next? And once we encapsulate within the VXLAN tunnel, now we can apply any kind of policies on this tunnel in there, right? So the endpoints becomes like, whether it's the host port and then the storage port, those becomes an endpoint. And within the zero trust model, what you do within today's in the Ethernet data centers, you don't trust anybody, right? So you have to explicitly configure the ACLs, access control list, to allow those two to talk to each other. In fiber channel, it's very simple. The zoning is there, right? Exactly what it does. The switches make it a hardware-based zoning. In IP world, when you're doing, for example, NVMe TCP, what do? So how do you create the ACLs in there? So this is, again, I'm showing you here is an ACI APIC controller architecture where endpoint grouping to the other endpoint, you can create a contract on it, and then you say allow that communication to happen next. And then that will be automatically pushed onto entire network. And on the contract, you can say what kind of a performance characteristics you want. And hence, you can take the current existing technologies for zero trust within the Ethernet, apply it to the NVMe-oF, for example, in NVMe TCP. So that will end. And back to you, Tim, unless, Rob, you have anything else here?
I don't think so. I think, the only thing would be to mention that there's new standards that'll enable NVMe over fabrics to be the security to be standardized across all the different vendors.
Great, thanks, Rob. Thanks, Kamal. Yeah, and we do have quite a few questions, so let's see if we can jump into those right away, so we can see if we get through majority of those in the next 7 minutes. So the first question is, if my HBA or fabric does not support NVMe over fabric in the SAN environment, what will happen here? Will the host see the lines?
So if you look at in the SAN environment, the only thing you need on the HBA is the code, right? You need the NVMe driver code in there, loaded in there, right? And the reason for that, as I went through it, when the whole init process happens, that NVMe driver has to be registered and then as a block device, and then so you can access that, right? So, and the way you connect on NVMe on the fiber channel, you'll be like, for example, so if you do not have, to cut the answer short, you will not see the NVMe namespaces, right? You will need that driver to be loaded on the HBA, yes.
One of the beauties of NVMe over TCP is that it can work on legacy systems because it's just a sockets application, basically. So depending on the operating system, I would imagine that there's probably an NVMe over TCP driver available for yes, even older NICs, as long as they support sockets.
Yes. And at the same time, the NVMe over fiber channel is also supported on the existing fiber channel infrastructure, because that does not, it's just a mapping on top of the existing fiber channel. So though no changes required on the switching perspective, it's just the drivers on the host adapter or the storage adapter. Thanks.
Great, thanks guys. Real quick, next question. NVMe over fabric benefits compared to SCSI MQ implementations. Are there any?
So SCSI MQ is a recent implementation, right? I mean, it's been a few years. Earlier, there was it was a single queue, right? That becomes a bottleneck within the SCSI architecture. NVMe, by nature, is a multi-queue, right? 65,000 queues in there. And practically speaking, I have not tested the SCSI multi-queue, but that's not the only aspect of NVMe when you talk about it. Is SCSI command sets are huge. NVMe, I think you barely need about 20 commands to get going. That's why the whole controller is put on the SSD itself. There's no SCSI controller, which becomes a bottleneck. That's why those SAS and SATAs have a bottlenecks. So there's much more advantage. As I said, we're solving the multipathing. We're going into multi-queues, into computational storage, transport mapping. So a lot more advantages in there than besides just a multi-queue within the NVMe.
Nothing to add to that, Tim.
Great. Okay. Next question. This might be for you, Rob. Should Rdma traffic preferably flow over separate VLANs or VXLANs?
I didn't hear the end of it, Tim. You kind of faded.
Oh, sorry. So within Rdma traffic, should you preferably separate those on VLANs and VXLANs?
It's not necessary, but if you want, a QoS for those, then you can certainly do that. So it depends on your performance requirements.
Next question is around security. And does any of these transports offer better or higher security than others? Are they comparable?
Yeah, I mean, if you look at the security, I mean, historically, on the fiber channels, just because physically they were designed as a separate network. and there are not too many fiber channel experts or hackers, really don't care about fiber channel. And it's a very tight control with hardware zoning, port-based zonings. You have encryptions in there, data encryptions in motion at rest and all that. So fiber channel being a separate network, there was less hand on it, so there was considered more secure. But again, at the same time, within the TCP architecture, and Rob can talk about Infiniband, there's a lot of security protocols there. I mean, over the years, industry has gone down to, as I talked about, zero trust and all that. So every protocol, every transport has their own, advantages of security. But security is something constantly being evaluated and innovated. Anything on Infiniband security, Rob?
Yeah, I would just add Infiniband's basically the same from the perspective of it's an isolated network, so there aren't as many people that know how to hack it. But on the one thing to add on the Ethernet side is, since it's much more widespread, it has a whole lot more security features and a whole lot more security experts. Of course, the other side of it is it has a lot more hackers. But I think that, again, I would go back to your application and the amount of effort you want to put into the security. If your application needs some, 200 gigabit bandwidth, you aren't going to get that from fiber channel. If your application your current applications are already on fiber channel, then you probably don't, unless you've got some dramatic needs, don't want to move them to dramatic performance needs. You don't want to move them because the cost of, throwing away your whole fiber channel infrastructure is probably prohibited.
Yeah, and also just to add to that, Rob, the fiber channel industry, not only because the fiber channel been around for a while for the storage with the SCSI and now with NVMe, but it's also with all the storage vendors. Take any one of them, all the IBM, EMCs, Hitachi, whatever, HP, NetApp, all of them certified the solution together, and that's why the customer, when they deploy fiber channel, they know they're getting something very verified and certified. That's another advantage why people stick there.
Okay, I think we've got time for one more question. This is our track record on CNAs is not great. Should NVMe fabric traffic flow over separate NICs and ports?
The first part was on our traffic.
Yeah, there's just a little bit more of a record. I guess they're having some issues with CNAs, converged network adapters with the traffic flow. I guess when they have a converged environment with so what they're saying, should they separate the NVMe fabric traffic?
No. Okay. Yeah.
It's certainly something you can do, but it depends on the capabilities for quality of service and in your environment. But that's the easiest way to get QoS, right? Is to have a separate network, but it's not necessary if you have the right kind of quality of service capabilities in your system.
Yeah, and I think if you look at the whole converged industry, they use the CNAs, and it's perfectly, you can do the PFCs, QoS, you can very well do with CNAs, all works out very good.
Great, thanks guys. We're just a little bit over the hour now, so we're gonna have to cut at this point, but great presentation, lots of feedback from everybody, and appreciate the in-depth dive from both Kamal and Rob. Excellent presentation. Again, we will be posting copies of this presentation up on the Nvme Express website. It should be up shortly for you guys if anyone wants to download this. We appreciate you joining us for part 2 of this session coming sometime in the near future. Thanks and goodbye, everyone.
Thank you.